Let's solve for the unknowns here. We're given a circle with the cyclic quad in the middle of it. So the unknown here, the first one is x here. As soon as I see a bow tie in the diagram, the first thing I look for is angles in the same segment. But before I do that, I can just look at x. I can see that x is part of, it's coming out of this diameter here. And the good thing about a diameter is we know that the diameter subtends an angle of 90 degrees at the circumference. So it means that this angle here should be in total 90 degrees. So if I have 20 on the other side, x should be 70 degrees. And my reason is angle in a semicircle. Next, if I want to solve for y, I can see that y and x are in angles in the same segment position. So it means that y is equal to x and x is 70, which makes y equal to 70 as well because of angles in the same segment, the bow tie. Now z, I can see that z is outside of my cyclic quad. Another word for outside is exterior. So I look for exterior angle of a cyclic quad. So the exterior angle of a cyclic quad is equal to the interior opposite angle. So opposite angle C1 is angle A. And I know that angle A is 90 degrees we determined before. So angle Z will equal to 90 degrees. My reason is exterior angle of cyclic quad is equal to the interior opposite. Let's look at another one. So name 4 other angles equal to x. We can see x here. X is in between this tangent and in between this chord BD. So in between tangent and chord, that would lead us to tan chord theorem. So tan chord theorem, we need to find 4 other angles equal to x. So let's look at tan chord. Tan chord means we need to see which angle the chord subtends at the circumference. So if I pull that across, I can see that x should go where C is. Also, if I look at tan chord, I can pull it across here. Pull the chord across, the chord BD, across to the circumference. So x should also go here for A. So let's start there. So we can say that angle A is equal to x because of tan chord theorem. We can then say angle C is equal to x. We can say tan chord theorem again, or we can say angles in the same segment because they are in that position. We can then look at, we need to find another angle for x. So if I look at angle A, I can see parallel lines, so I should look for alternate corresponding or co-interior angles. Because of this crossing lines in the middle, I'll look for alternate angles. So angle A is equal to angle D, I can see, because of alternate angles. So angle D should also be x. Then if I look at angle B is equal to angle D because of angles in the same segment. So angle B is also equal to x. So those are my 4 angles that are equal to x. Let's now prove that AD times DE is equal to AE times DC. When I see this type of question, I usually look for proving similarity. So I need to choose 2 triangles that have AB, DE, AE, and CD in them. So the 2 triangles I've chosen are triangle ABE and triangle DCE. So we need to prove that those 2 triangles are similar. So I can see angle ABE, this top triangle, and triangle DCE, the bottom triangle. I can see I will get vertically opposite angles here with E. So I have it here, AEB is equal to CED, that's vertically opposite. We also showed alternate angles before. So ABC, angle ABC, which is here, is equal to angle C, which is there. Those are alternate angles. We did prove those equal before. And also angle BAD is equal to angle CDA. also alternate angles, or you can just go with remaining angles of a triangle. As long as you have two angles, the third one is automatically equal. So we can then say that triangle ADE is similar to triangle DCE because of angle, angle, angle. So from the similarity now, we need to work with the sides. AB, which are the first two letters here, over DC, which are the first two letters there, will equal to AE, which is the first and last, over DE, which is the first and last there. Cross multiply those, and you'll end up with AB times DE is equal to AE times DC.